Training modern artificial intelligence requires processors to perform trillions of mathematical operations every single second. For centuries, computation meant physically manipulating tools, like sliding wooden beads across rods. As mathematics grew more complex, engineers built intricate mechanical engines, relying on the physical rotation of brass gears to automate calculations. The transition to electronic logic removed the moving parts. Engineers used vacuum tubes to control the flow of electricity, though these systems consumed massive amounts of physical space and power. The solution arrived with the solid-state transistor. By manipulating semiconductive materials, logic could finally begin to shrink. For the last half-century, the primary strategy for advancing technology has been simple miniaturization. Engineers learned to etch these silicon pathways smaller and smaller, eventually fitting billions of them onto a single integrated circuit. Transistors are now approaching the size of individual atoms. At this scale, electrons begin to leak unpredictably through physical barriers, a phenomenon known as quantum tunneling. Miniaturization has reached a hard physical limit. To meet the demands of modern data centers, we currently push vast amounts of electricity through microscopic, rigid pathways. This brute force approach generates intense heat and consumes massive amounts of power. This bottleneck has forced researchers to ask a different question. Instead of expending energy to make a machine simulate the laws of physics, we can allow the laws of physics to perform the work directly. Moving away from traditional digital logic leads to the study of fluid dynamics. This is liquid computing, a practical case study for a post-silicon world. Without a traditional processor or software code, physical wave interactions within a liquid can process complex mathematical patterns. The process begins with a dynamic input, like human speech. To enter the liquid, the audio signal must first be translated into physical movement. A piezoelectric actuator receives the electronic signal and vibrates. These precise movements are injected directly into a liquid reservoir, generating ripples on the surface. As new ripples enter the pool, they collide with existing waves. Through superposition, these frequencies combine, creating exact points of constructive and destructive interference. This overlapping gives the liquid a natural short-term memory. Its current state is a product of previous inputs. This inherent memory is why liquid reservoirs excel at processing time series data. They track continuous speech, analyze heartbeat ECGs, and calculate balance for robotics. While the mathematics occur inside the reservoir, extracting that answer from a moving liquid surface is a significant logistical challenge. Scientists solve this using an optical readout. Precision lasers are aimed at the reservoir, bouncing off the fluctuating angles of the liquid surface. High-speed cameras capture these scattered laser reflections. Because every input generates a distinct wave pattern, the camera records a unique physical fingerprint for every signal. Traditional artificial intelligence is still required at the end of this process. However, instead of performing heavy mathematical calculations, a simple, lightweight output layer is trained exclusively to classify these optical fingerprints. The technology remains experimental. Because the computation relies on fluid dynamics, the systems are extremely sensitive to environmental vibrations and temperature shifts, presenting massive manufacturing hurdles. GPUs remain necessary for the high-precision digital arithmetic of large language models, while liquid reservoirs specialize in the hyper-efficient processing of dynamic sensory patterns. Liquid reservoirs represent one part of a broader field known as physical computing. In photonic computing, engineers replace electrons with beams of light, allowing for near-instantaneous data transfer across optical chips. Neuromorphic engineering physically mimics the neural spiking architecture of biological brains to drastically reduce energy consumption. Meanwhile, DNA and quantum computing utilize spatial chemistry and subatomic probability to solve specialized logic problems. The future involves a diverse computational ecosystem, leveraging different physical properties for their unique strengths. A theoretical AI supercomputer in 2050 would be a hybridized machine. Digital math, photonic communication, and analog liquid reservoirs would operate in total synergy. By offloading sensory processing to these physical substrates, we can reduce the reliance on power-hungry GPU clusters, allowing AI to integrate into global infrastructure with a significantly smaller energy footprint. Long before humans built calculating machines, the universe was performing complex computations through the raw laws of physics. The next stage of engineering involves moving past digital simulation to build systems that compute through nature itself.